Okay, so apologies to those of you who might have been expecting to see Meg here, but I'm doing it instead. You'll see why in a minute. We're coming from the kind of fringe of Metal Earth in a project that we now call Metal Oceans. And the purpose of the project is to interrogate modern tectonic settings and to compare them to ancient ocean crust, including in superior greenstone belts. The starting point is basically that the understanding processes in greenstone belts has always been influenced by comparisons with modern analogs, but the quality of those comparisons is only as good as the geological maps that are available. And for the most part, we don't have any geological maps of the modern oceans. Lots of cartoons, but not geological maps. And that's what this project is really trying to change in order to make those comparisons with the ancient crust. So the team is big. It's spread across Canada and Germany. Almost everyone in the team here is basically making geological maps, mostly in areas of the ocean crust that have never been mapped before, and at scales that we can directly compare with ancient terrains. A few people have been there from the beginning. Meg was a pioneer, but now we have at least a dozen people mapping in different localities and in different modern tectonic settings. The project is massively leveraged because of the nature of some of the work that we do, in particular going to sea. And so in addition to Metal Earth as our primary partner, we are very closely allied with GeoMar, which is the Helmholtz Center for Ocean Research in Kiel, Germany. And more recently, we're working in an image create program, providing some of the critical training that is required to make some of these seafloor maps. What we're mostly interested in is identifying crustal growth in the oceans and what it might have looked like in the past. And in particular, the pulses of crustal growth that are directly linked to mineral deposit formation. In this case, this shows the distribution of VMS deposits through time, closely linked to major pulses of crustal growth. The challenge has always been that the record of crustal growth is not that well constrained, getting better, but not that well constrained. And even so, the episodes of ore formation, the specific episodes of ore formation, occur at relatively short timescales compared to our understanding of crustal growth. So the question is, can we better identify or recognize the short bursts of crustal growth that predict where and when these major ore forming events occurred? And so those are the main questions for the project. What the pulses of crustal growth look like? Can we better constrain the time and space scales of those pulses of crustal growth, which are basically opening of basins, coincident with major ore forming events? And can we link that to mantle properties, which I've been hearing a lot about? And can we identify ancient structures that could have controlled mineral endowment during those episodes, not only VMS deposits, but possibly also later gold? To address this, we chose a study area, which is really a modern day center of crustal growth at the edge of the Indo-Australian margin. This is some of the fastest growing crust on Earth today, and it includes some super endowed terrains with some of the largest copper and gold deposits in the world, and also the highest density of submarine hydrothermal activity pretty much anywhere in the oceans, centered in the northern Lao Basin, the Fiji Basin, and the Bismarck Sea. The Lao Basin is a little bit unique among this group of environments because it has the highest predicted mantle temperatures in the Western Pacific based on or inferred from seismic velocity models. So if ever there was a place we wanted to compare to Archean greenstone belts, this is probably it. Our approach in the project has been virtually identical to that of Metal Earth. We're using a transect approach to produce the first really multidisciplinary geological and geophysical maps of these areas. Now in three main areas we're working in: the northern Lao Basin, which I'll mostly talk about today, the North Fiji Basin and the marginal basins of easternmost Papua New Guinea. Our first dedicated Metal Oceans cruise was in the Lao Basin in 2019, just before the pandemic. And during that cruise, we mapped an area of about 50,000 square kilometers of the Lao Basin Backarc with full-on multi-parameter geophysics. It took we were at sea for 2 months, and it took this number of people to implement all of the geophysical surveys that were undertaken. And that's the data set that we are now basically plowing through. During this cruise, we learned a lot about Backarc Basin evolution. I think that some of us really didn't fully appreciate, and that's what these pulses of crustal growth in the opening of the basin really look like. Our old view of crustal growth was basically Backarc, similar to the southern Lao Basin, basically uniform spreading fabric emanating from a single Backarc spreading center, producing crust that's basically miles of monotonous Backarc Basin basalt. This is what we thought of as pulses of crustal growth in Backarc Basin development, until we started working in the northern Lao Basin, which is completely different. And it has a wide range of forms of crustal growth, from arc rifting to intraplate volcanism to plume sources, and widespread extension simultaneously over the entire width of the basin. And all of that is bound by these major crustal scale, we think crustal scale faults, several hundreds of kilometers long, that basically separate two domains of the Lao Basin that have completely different evolutionary paths. What we figured out pretty early on was that if we're going to try and understand this, we're going to need a geological map. And so we set out to create the first assemblage level geological map in the oceans, in fact, at 1 to 1 million scale. And this was led by Meg. And this turned out to be nearly a 2-year journey, because one of the things we had to do at the beginning was to teach ourselves how to make these maps. And for that, we borrowed heavily from remote predictive mapping techniques on land. The result is the map that has just been published by Meg in Geosphere, and it came with a massive compilation of geological information that Meg collected, that was used to break out about 40 different formations, geological formations going back at least 30 or 40 million years through the history of the crust at the Indo-Australian margin. I'm going to talk a bit about this map later, but right now I think we can't overstate the importance of this map, because what we had before was effectively or equivalent to a map of the province of Ontario, with the only geology being the sub-province boundaries. That's basically what our map of the Lao Basin looked like before we produced this, and I'll talk about it in a minute. Our first transect, our big cruise to the Lao Basin, included about 1,000 kilometers of new seismic reflection and refraction data that spans the entire distance from the arc all the way to the very end of the Backarc and the big crustal scale faults. This is a very different approach to what is normally done in Backarc environments in the marine geology world. Nearly all studies of this type are focused on the arc front and the trench. Everybody wants to image the slab. And not much attention is actually paid to the accretion of the Backarc crust. So it's something completely different that we were doing. And these data are giving us a much better impression of what Backarc rifting and basin opening looks like now in quasi 3 dimensions. The really complicated geology of the northern part of the Lao Basin has also been partly unraveled last year by Alan Baxter, who's in our group. And Alan analyzed about 700 shallow earthquakes in the area and used that data to classify all of the faults, about 300 faults in the northern Lao Basin. And the most interesting outcome of this story was that the majority of the faulting is either strike slip or oblique, and rather than normal faulting, which is what you would have expected in a rift basin like this. And this really reflects the trajectory of the Pacific plate as it impinges on the arc, and the predominance of microplate rotation in this very complicated northern part of the Lao Basin. Identifying and classifying those structures was a major step forward in defining the microplate architecture. Up to this point, the geology of the northern Lao Basin was basically described in terms of only 3 plates: the Indo-Australian plate, the Pacific plate, and then a central plate in the middle of the Lao Basin. But suddenly, with the work that Alan and Meg have done, we've got 7 microplates, some of them with dimensions as small as 100 kilometers. And from this, it's clear that the northern part of the basin did not form from one spreading center, as in the south of the basin, but has been forming at least 7 different spreading centers, all operating, all opening at the same time. This is what a major pulse of crustal growth looks like. And basically, it's a microplate factory. And the hallmarks of the formation of these microplates are triple junctions. These are a necessary consequence of the plate fragmentation. And there are potentially half a dozen triple junctions emerging now in the northern part of the Lao Basin. And it's something that we're really interested in looking at in ancient greenstone belts, because these are major magmatic centers of magmatic activity as well. I'll say a bit more about that in a minute. This is the same map showing the architecture of the spreading centers in the northern Lao Basin with 7 or 8 of these localities. The important observation, or an additional observation, is that in order to accommodate all the plate accretion that's occurring, you need some major transcurrent faults to effectively take up the slack and make room for all the new crust. And there are at least 3 of these major faults in the northern Lao Basin. The one that separates the basin, I showed you early, this is called Peggy Ridge. It's it varies from transform to transtensional. And another one is the Fiji transform, and another is the Futuna deformation zone. These long-lived structures are required for the hyperextension and the runaway crustal growth that's currently happening in the northern part of the Lao Basin. This is a blow up of Meg's map, and it shows these major spreading centers all in orange here. And the combined length of all of these spreading centers in the North Lao is about 1,000 kilometers, the cumulative length of all that spreading. But that's in a basin that's only 600 kilometers wide. So in terms of the amount of spreading per square kilometer of Backarc Basin, we're basically, there's nothing like this anywhere else on the planet as far as we know. The clear message is that if you want to make a lot of crust in a short period of amount of time, you do it with 7 spreading centers and not just 1. And you make sure that you have the necessary crustal structures to accommodate that growth. These are the things that we need to look for I think, in greenstone belts at the appropriate scale. So this is Meg's reconstruction of the assemblages and Alan's analysis of the assemblages that make up the Lao Basin. And their work really answered a couple of key questions we had at the beginning. And they were, what are the locations of the microplate edges? What are the structural and magmatic controls on these pulses of crustal growth? And where and when do those pulses of crustal growth occur? A characteristic feature, which is illustrated schematically by the black triangles here, is that there's simultaneous growth of different assemblages represented by these bars here, in different locations at the same time. This to me sounds an awful lot like the geochronological framework of the Abitibi Greenstone Belt that I've been hearing about for the last day and a half now. And perhaps this is really not a bad model for some of the crustal growth in a greenstone belt like the Abitibi. If you consider the entire history of the Lao Basin going back to and including the older arc basement, the total age range that's included in that storyline is not that different from the Abitibi assemblages, which are just tacked on here for comparison. this is something that Meg would never do, which is why I'm giving the talk, but I'm closer to retirement, so I can afford to take the risk. But essentially it shows that a number of the major key assemblages like Kidd Monroe, Tisdale, Blake River, they would easily fit in the time span of the opening of the Northern Lao Basin, with crustal growth similarly distributed over a number of different locations at the same time. This is what the crustal growth looks like or the assemblage map looks like from Meg. The most recent pulse of crustal growth has actually produced 9 different assemblages shown in pale green here, and an area age plot of those assemblages shown here in purple basically shows an early stage or early episode of slow crustal growth, and then a surge of fast growth coincident with the appearance of the Peggy Ridge fault zone, the large crustal structure that basically separates the Lao Basin into 2 different parts. Perhaps this is a simple explanation for metal endowment, because we believe that this area is significantly more endowed than in the southern Lao Basin, and that perhaps we're looking at endowment being linked simply to rapid changes in crustal growth. Another person in our group, Caitlin Brecker, is currently introducing this microplate and assemblage model into G-plates, which is a software that calculates the responses to global plate motions. And she's actually reproduced the growth curve from first principles of global plate motion based on the architecture of the microplates in the Northern Lao Basin. So we're confident that what we're observing in detail at least makes kinematic sense in a larger regional context. We're also looking at the about 1,000 kilometers of high resolution sediment profiling, which is something else that people don't really do much in the Backarc Basin world. And this is allowing us to identify the architecture of the microplates from, for example, the arc rift at Funalai all the way to one of these major, we think, crustal scale faults. And early on, early interpretations of the refraction data on the same line across the arc to Backarc transition show clear excursions in the top of the mantle that are probably linked to the geometry and the edges of these microplate domains, with deviations of 2 to 3 kilometers or more in the position of the top of the mantle. The velocity profile is also pretty choppy, and this is currently being worked on by Florian Schmidt, who published this section last year. And it's far from uniform. It's clear that the composition of the Backarc crust is anything but uniform. This is something that our group is working on now. Mark Fassbender, a PhD student, is looking at all of the geochemistry in this area. And he sees a full spectrum, both mafic and felsic rocks, a full spectrum of compositions that are not too different from Abitibi assemblages, at least for some of the microplate domains. And I think one of the more intriguing aspects of this part of the Lao Basin is a very large mantle plume anomaly recorded not only in the rocks, but also in the hydrothermal fluids, exactly at the location where the Peggy Ridge transform intersects the Northwest Lao spreading center. There's a strong mantle helium isotope signal in all of the rocks from this location, suggesting a sudden release and enriched mantle material coinciding with these pulses of crustal growth. The group now is focused really on much higher resolution mapping to make closer comparisons with the assemblage level maps, for example, in the Abitibi Greenstone Belt. And we're particularly trying to better understand the controls on major magmatic events, looking at voluminous magmatism, for example, at triple junctions that occur at those plate boundaries, at those microplate boundaries, including large shield volcanoes, the central volcanic complexes of the triple junctions, and even some magmatism which is occurring on some of those large, what we think are crustal scale structures. We think that some of these centers shown to scale relative to the Abitibi, we're now mapping at 1 to 1/4 million instead of 1 to 1 million, these can be potentially compared to different parts of the greenstone belts. And the goal here, we've currently got students working on about 7 of these. The goal is to build type sections and attributes tables to compare directly to possible analogs in the greenstone belts, obviously with big question marks at this point. Our second large area that we're working in is at 1 to 1 million scale is in the marginal basins of the eastern Papua New Guinea. This is a map that similar to Meg's map that was produced by Philip Brandel and is in prep right now for publication. This is a particularly interesting region because it has 3 basins, 3 completely different basins that are all about the same size as the Abitibi Greenstone Belt, ranging from essentially barren oceanic crust all the way to rifted arc crust. We have a cruise currently approved and funded to go here. And in fact, we were supposed to leave in 2 months, but that's been canceled because of COVID, and we're waiting for rescheduling. So some conclusions. What have we learned? A few things about the characteristics of what is probably the most productive crust in the oceans in that northern part of the Lao Basin. Here, the major pulses of crustal growth are characterized by Backarc crust that forms simultaneously at many different centers in response to distributed extension and intraplate magmatism. The microplate breakouts and the triple junctions are part of an accelerated basin opening that has to be accommodated by large-scale transcurrent fault zones. You just can't do it any other way. And the Backarc crust is neither entirely oceanic nor entirely arc-like, with the probability of extensive overprinting and inheritance, some of which we've already heard about, although in thicker crust. The mantle input occurs at intersections of these translithospheric fault zones, and especially at the emerging triple junctions. And there is intense crustal scale deformation in this, what we think would be equivalent of well-endowed terrain, which contributes to the abundance of magmatic and hydrothermal systems. So this is where we started. And I think we're making considerable headway into identifying the details of the endowed crust relative to the less endowed crust, and hopefully we can compare that to the Abitibi in the coming months and ahead. So that's it. Answer some questions, maybe.
Great, thanks very much, Mark. Yeah, we have a couple minutes for live questions from the audience here.
I have a couple if nobody else does.
Go ahead, Graham.
Yeah, that's fascinating, Mark. So there's that massive oroclinal bend on just around Fiji there, and I can't. I guess I'm not smart enough to work out what the interplay of that is with the structures you see and the plumes. So we actually have some mantle xenoliths from one of the Fiji islands close to that bend, and we can clearly document a lithospheric loss event from there that we think is the plume. So do you think it's lithosphere softening and causing that bend, and a lot of the structures you see are responding to that, or are they two different things?
You're talking about this bend?
Exactly. I mean, when you zoom out, it's one of the biggest structures you can see in the entire Pacific, that bend.
Yeah. If you reconstruct you go back 20 million years and you reconstruct the changes in the plate motions and fragmentation following the collision with Ontong Java, you'll see that the Fiji platform, which is basically connected to the elbow at that bend, it rotates through almost 90 degrees. And it's exactly at that point where probably about 5 or 6 million years ago, where that elbow was actually oriented more or less like this, that the Peggy Ridge transform just pops up. And so it's absolutely controlling the later evolution of the I think. I shouldn't impose my biases on the rest of my group, but I think that it's absolutely controlling that episode, that big pulse of crustal growth along the length of of this transcurrent fault.
Hi, Mark. Andy Worth had a quick question. There's a lot of alkalic magmatism in Fiji, and I'm just wondering how much alkalic magmatism do you see offshore, and does that continue, or do you even have that data yet?
No, we don't really have that data yet, Andy, but I wouldn't call it alkalic, but there's clearly, you know, enriched mantle material in that portion of the northwest part of the Lao Basin that I talked about. But it's nothing like what you see on the island of Fiji itself, you know, Emperor and so forth. We had one project where we were trying to integrate, and we still need to do this. It was just an honors thesis where we tried to integrate that history of Fiji itself, and particularly its structure. You know, we're obviously interested in the Emperor gold mine, but we need to revisit that.
Thanks.
Okay, Mark, there's one from the chat room here. Do you know what the dip and depth extent of Peggy Ridge is?
Dip is vertical. I can show you a really peculiar, I don't want to take up too much time here, but I'll go back to the, this is one of the sections that goes from the arc through the current arc rift into the Backarc Basin, and it just clips the edge of Peggy Ridge. And that is the seismic response of Peggy Ridge, which is basically a shear zone. I was surprised when the seismic guys showed me this, and I said, I thought you couldn't pick up vertical structures, but anyway, they showed us this. So it's vertical. But we don't know how far down it goes. I guess, you know, it's 400 kilometers long. I have to guess that it's the full length of the or the full depth of the crust.
Great. Okay, thank you very much, Mark. Appreciate that.